Okay, I'm going to start the homework on page 380 from section, I think it was 8.6, I think. Yeah, 8.6. So they ask you to find an equation that has these numbers as their roots, x equal -1 and x equal 5i. So the thing you have to remember, though, is when you have a complex root, they always come in pairs. So, and they're conjugate pairs. So if x equal 5i is a root, then also you have another root, x equal minus 5i. So altogether we have 3 roots. So, like we've been doing before, if x equal -1, then x plus 1 is a factor. And x minus 5i is a second factor, x plus 5i is the third factor. Now, this is our function, okay? Or if they wanted us to write it as an equation, I think that's what they actually said this time, I would write it as equals 0. Now let me show you how to multiply this together in the easiest way. You always want to start by doing these conjugates first. So I'm going to just let this guy tag along. And when I multiply this together, I'll do first, outer, inner, last, of course, to FOIL, but I'm going to remember that these are conjugates, so I get the difference of squares. So I'm just going to get x squared minus 25i squared. But of course we remember I squared is a minus 1, so x plus 1, don't forget to equal 0, times x squared plus 25 is equal to 0. And then I can FOIL this remaining portion, x cubed plus 25x plus x squared plus 25 is equal to 0.
Hello. Hey, Mort,
hi guys.
With us?
Of course, this one didn't end up in correct standard form, you know, where the x squared is in the wrong order, but I'll let you fix that. All right, here's number 5. There's a really nice shortcut to this. They've given us 2 of the roots. They want us to find the third root. We know there are 3 roots altogether because of this x cubed is the degree of the polynomial. So there's only 3 roots to talk about. Here's one real root, the 3, and here's a complex root, or a purely imaginary, but its complex conjugate will also be a root. So we could simply answer this question by saying the last remaining root is x equal -2i, the complex conjugate of this first imaginary root. But I want to take a minute and show you how to do synthetic division with imaginary numbers, because I'll probably ask you to do a bigger question where you'll take out the imaginaries. You'll be left with a quadratic that you could then solve. So let me just do this imaginary root first. So 1, -3, 4, -12, synthetically dividing with the imaginary root 2i. Now, you have to be careful, and this is where I talk about making sure you've spread out these coefficient numbers so you have enough room. Bring the 1 down. When you multiply, it's simply 2i. But here's where it's interesting, because when you're adding this column here, those are not like terms. So -3 plus 2i is all you can do. Now, over on the side, I have to multiply 2i times the -3 plus 2i. I've got to multiply that out. So let me do that over here so I have some space. -6i plus 4i squared. Oh, but remember what I squared is, so that becomes -4 minus 6i. So I'm going to put that answer here, -4 minus 6i. You start to see why I wanted you to space things out. Don't put your numbers so close together. Now when I add this column, okay, I'll put the answer here. Let me divide up my columns neatly. I'm going to add these together. The 4 minus 4, of course, cancels, but I am left with a -6i. Now I have to multiply these two together, 2i times a -6i. It's going to be a -12i squared, but of course we know what I squared is, so this becomes plus 12. So a plus 12 goes here, and I do indeed get that 0 remainder because that was a root. Okay, let me erase this. Now I need to take out a -2i. Let's say I wanted to try this again. And I'm going to factor out the negative 2i, because I find there's a plus I, there has to be a negative 2i. So, bring down the 1, multiply these together, add these together, these are going to cancel, negative 3, multiply, plus 6i, and indeed I get the 0 remainder. Those are both good roots. When I'm looking for that remaining root, which pretend we didn't know that it was going to be 3, I would put my x's back in. X minus 3 is equal to 0, and obviously x equal 3, I just found the last remaining root. It's just another way to do that same problem if they'd asked the directions a little differently. Okay, number 13, they're asking us to give the nature of the roots. So we're not solving it, we're not going to find values of x, we're just going to tell you, is it imaginary, is it real, is it positive, is it negative, that sort of thing. No solution. So we're going to use Descartes' rule of signs. So we're looking for, there's our function. It's here being set equal to 0, but we're looking for the sign changes. So remember, this was implied positive in the front. So from here to here, there's no sign change, but from here to here, there was one change. We went from positive to a negative, so that's one sign change. So I would say there was one positive real root. Now, normally we would say, you know, the number of sign changes, or you could do the number of sign changes minus 2. I'm not going to do the minus 2 in this case because that would put me into a negative number for the number of roots, which is ridiculous. We don't go negative number of roots. So I have one positive real root, but then remember, I have to evaluate what f of negative x is. So if this was my function, set equal to 0, to figure out what f of negative x is, I put a negative x in for every x. So negative x gets squared minus 4. So what happens is when it's even powers here, like the 4, then the negative sign becomes positive, and I just have x to the 4th. If you want to put the plus, you can. Same here, I've got an even number, so when I square a negative, this negative here goes away, so it's 3x squared minus 4. Now look at the number of sign changes. From here to here is not a sign change. From here to here is one sign change. So guess what? I have one negative real root. Now here's where I like you to make the table. So I'm going to actually erase this for a minute and put that somewhere else. And one negative real root. Okay, I need a little space to label my table. Here I'm going to put the total number of zeros. Here I'll put the number of real positives. Here I'll put the number of real negatives. And here I'll put the number of complex zeros. Remembering that those always come in pairs. All right. The total number of 0 comes from the degree of the polynomial. The degree of our polynomial is 4, so the total number of zeros is 4, and that's true always. Now, going back to the number of positive reals, we had said there was 1. So the only option here is a 1. So whatever I do, there's going to be a 1 here. The only option you have for negative real roots is a 1. So this is always going to be a 1. So actually, we only have, you know, all our rows are going to look alike. Because remember, you have to add up all these columns, these 3 columns on the right, and they have to equal 4. So far I only have 1 plus 1 is 2, so I need another 2 here. There's no new information, there's no new here, so I'm going to get rid of that. So now you can see I can have 1 real positive, 1 real negative, and 2 complex zeros. And this right here will work as our answer.